So let us talk about the algorithm. Now we will discuss this algorithm in detail, and then we will also apply this algorithm on one scenario to understand that how it actually works. So the basic idea of algorithm is it finds an edge of the least possible weight that connects any two trees in the forest. So we have to start with finding the edge which has a minimum weight. It is a greedy algorithm as it finds the minimum spanning tree. So every time we are always looking for the edge which has a minimum weight, and we keep on moving with this strategy unless we connect to all the vertices, unless we cover all the vertices. Now when I say edge consists of two vertices. At the two ends we have vertex, so we have to pick these edges. So in this Kruskal method we are focusing on the edge. We keep on picking these edges, and once we find that all the vertex are being covered, then we will stop, and the final result will be your minimum spanning tree. So how actually it works, we will go with this algorithm. Now here you can see with this algorithm you need to pass your graph and also the weight of each edges. So you have to actually pass this thing, G equals to VEW, your vertex edges and the weight status of each edge. Now here you can see we are using two procedure. One is called make set and the find set. So first we understand what is make set and what is find set, then we will start discussing this entire algorithm. Okay, first let us understand what is make set. So make set, let us take an example. This is your graph, let's say A, B, C, D, something like this. Okay, and when I say make set V, that means for all the make set V means it will treat these vertex as a set. So it will treat this as a set. So if I say for each vertex that belongs to this graph make set V, that means we have this set vertex with defined as A, B, C, D, E, and when I say make set V, actually I am trying to represent each vertex as an individual set. This is the job of make set procedure. Then we have something called find set. Now here we are representing, let us write here find set. Now here we represent every set. So let's say we have a set A, B, C, D, E. We represent every set by one leader. We call it as a set representative or a leader. So every set is represented by a leader, or we have one representative of that set. Now that can be anything, it depends on the logic. In general, we use the first element. In many of the algorithms you can find that the first element can be used as a representative, but this is not mandatory. You can use any one, it depends on your logic. So let's say I am using the first element as a representative of the set. What does it mean? It means if this set is A, and if I say find set, so the find set will return the leader or a representative of the set. It will return. So if I say find set A, then it will say the answer is A. In general, the default procedure is actually takes input as a vertex, not as a set. So we will follow with the default procedure, but it's up to you. You can also modify its significance, but the default procedure says you have to pass one vertex in this find set, and then find set will return the leader of that set. What does that mean? It means I have two sets. Let me make one more set to understand in a better way. This is set A. Let's say this is set K, which have value list E, F, G, H, P, and I am assuming that this is the representative or leader of the set. This is the representative of this set. Now, if I say find set A, my answer is A, because the leader of the set for which A belongs is also A. If I say find set D, or find set C, or find set E, all my answer will be A, because the representative of the set to which these vertex belong is A. Now, if I say find set H, in this case my answer is E. Find set P, my answer is E. So when I say find set, it will return the leader of that set. This is the meaning of find set. So what is required here? First we have to pass the graph along with the weight. We are taking one set A, which is initially empty, and then we will apply the make set procedure. So let's say this is our graph A, B, and C, and we have the vertex 1. This is edge 1, 2, 3. This is the weight of these edges. So the very first step is A is empty. For each vertex, that is A, B, and C, make set V. So I will apply make set and I will get A, B, and C. So we are calling this not as a small a because we are already using A here. So just to make it simple, we will use a small A, B, and C. So this is A, B, and C, and here we have set A, which is empty. Now this is done. Sort the edges of E into non-decreasing order via weight. So now you have to look to this graph and you have to arrange these edges in the non-decreasing order. So this is the minimum weight. So you write AB first, then BC, and then AC. So you have to arrange them in the increasing order, the minimum weight and then increasing. For each UV in G. Now for all, when I say UV means it's an edge. For each edge, so U means the vertex at the one end, and the V is also the vertex at one end. So UV means this thing. So this is a general term. So whenever I said any edge, it will always represent as a UV, where U and V represent these vertices of this edge. E ordered by weight UV increasing. So for all these edges which are placed in the increasing order, you have to check find set U and find set V. So you will pick one edge. Each edge consists of two vertex. You have to find the find set of this vertex and find set of this vertex. So you will say find set A and find set B. Now what we have understood, that find set will return the leader of this element. So now these are the set, this set, and this set. Now initially this set consists of only one element, this set consists of only one element, so obviously this is the one element, so this is representing as a leader, this is represented as a leader, this is also represented as a leader. So here if I say find set A, you will get A, and here if I say find set B, you will get B. So that means both are not same. So if both are not same, if you are getting a value which is not same, so here also we are getting value which is not same, we have to do this step. If this is same, then we will skip this part. What is required? A equals to A union UB. So you have to add this edge in this set. So you are going to add this into this. So what is the edge? Edge is AB. So AB you are going to add, and then you have to make union with the existing set. So initially there is nothing, so what you get, you simply get in the set A and B. So this is how this algorithm work. And finally, when you keep on working with all the vertex, because we are working for this loop, for this for loop, and for loop is working for all these edges. So here we have three edges, so you have to work for this, you have to work for this, you have to work for this. After completing all this, you will get your A, and that is your answer. Now this is how this algorithm will work. So we have just discussed a very rough idea that what are these steps. Now we will apply these steps in one numerical, and or you can say in one graph, and we can see that how the things are work and how to get the final minimum spanning tree. So let's take one example. Okay, now let's understand this Kruskal algorithm using one example, using one graph. So this is the algorithm given to us, and now we'll take one example here and we will apply this algorithm on this example to understand that how the algorithm works on any graph to give us minimum spanning tree. So let us, this is the graph given to us, A, B, these are the vertices. These are the weights of these edges given to us. Fine. So in order to apply the Kruskal method, you must have one graph with the edges. So we have to provide the graph along with the weights, and then we will take one set A, which is empty initially, which is null, and then for each vertex of this graph, so these are the vertex, for each vertex we need to make a make set. So when we make a make set for each vertex of this graph, we will get a set for all these individual vertices. So the make set will result this thing. So we will get these 7 sets, which consist of one item, one element, which represent the each vertex of this graph. So we have A, B, C, D, E, F. We can see this, these are the vertex here. Then sort the edges of E into non-decreasing order by weight. So then we will look into the graph and we will see, we will sort the edges into the non-decreasing order. So here you can arrange this order. So here you can take for the very first I'll take AB, this edge AB, whose weight is 1. Then I'll take AE, whose weight is 1. Now it doesn't matter that you can take AB or AE first. So I have chosen AB as the first edge. You may choose AE as the first node. So the end result will be the same. So either you can choose AB or AE. The final output will be the same. The only difference is you may get different structure of the tree. As we have discussed that when we find the minimum spanning tree, and for any graph we have various minimum spanning tree are possible. So the structure may vary because you may have selected the different edge while you started, and because of this difference your structure may vary, but one thing for sure that the final answer will remain the same. The value of the MST will remain the same. So then the next will be CF or FC, because this is undirected. So you can call it CF or FC. Both have the same meaning. And then we have FD, value 1. So we have chosen all the edges with weight 1. Then we go to the next value, that is 2. So BC is 2. Then we have AF 2. Then we have CD 2. So we have taken all the vertex, all the edges with value 2. Then we will take the next, that is BF 3. Then we will take ED 3, and then left is EF, which is 4. So you can count here how many elements we have: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means in the given graph we must have 10 edges: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means we have covered all the edges here. and this is also arranged in the ascending order. So we have finished with this step. We have made the mix set, we have sort the edges. Then for each edge, UV in G, so for each edges which is given in the graph, which is arranged in the increasing order, that means for every edge, so we have arranged these edges in the order, and then we have to perform some task because we are in the for loop. We have to do some task for every edge. What is required? Find set U is not equals to find set V. So whenever you pick any edge, so when you say AB, so when you pick the edge AB, so every edge consists of two vertex. So the edge endpoints are the vertex. So we have to find out the find set of A and find set of B, and if both of the vertex belong to different set, then only we will include this edge into our solution. So A is actually our final solution. So initially it is empty, and as we move forward, we can keep on adding the edges into the solution. So if they belong to different set, then only we are going to add into the solution, and then we will do the union operation. So let's see how the things will work. Now initially all the vertex are belonging to the different set. So when I say AB, so when you say find set A, and you find set B, so what is required? You need to pick an edge. I pick this edge AB. I will find set A and find set B. So find set A will, because this is the only element, and we discussed also already that find set means it will return the representative of the set. So it will return A, it will return B, and because A is not equals to B, that means this condition is true, and we move to the second part, and we are going to add this edge into a solution. That means this is to be included in our solution. So I'm going to write here A is set, which is initially empty. Now we have AB added into this set, and whatever the edges I am going to include, I am also marking it here. Then we have to do this for all the edges because we are in the for loop. Then we go to AE. Now E is this, already we have taken this set, is already been worked. We have already worked with this vertex. It's already worked. Now look at E. So if you look at E, E will give you the E, and when you look at A, so A will be here and you will get A here. Okay, so when I say find set A, now we are assuming that the leader is the first element of any set. So when I say find set A, and the A is actually the part of the set, and you will get A, and here it will get E. Both are not same. That means you need to include this into a solution. So AE is also going to include, and also we have to do along with the including this edge in our A set, we have to also do union. So when you move to next step, you are going to include this E into your set. Then comes CE. So C is here alone. Again, when you do find set C and find set F, now C and F are both independent, so you are going to get the value which is not actually same. So again, CF is going to be included, but when you write here, because CF is not a part of this set, so you are going to write like this, ABE. So in our solution set, so far we have included the edges ABE and CF, and this is also included. Then we have F and D. So you can see D is still here. So when you do find set D, it will return D, and when you do find set F, so F is here, it will return C. So D and C are not same. So again, this is to be included in our solution, and now we will be having this thing A, B, E, and because F, D, F is here, so D must be included in this set. Then comes BC. Now if I say, if I pick this edge BC, I need to find set B, and I need to find set C. Now find set B I can get from here, and it will return A, and find set C I will get it here, and it will return C. And because both are not same, that means this edge need to be added into a solution, and then because we have added here, so we need to do the union operation, and you will get here A, B, E, C, F, D. So far you can see that which of the vertex are remaining, because our final objective is to include all the vertex with the minimum edges. And not only minimum edges but the minimum cost edges. So we will move to the next. Now AF. Now A and F belong to the same set, so this is not included. CD, C and D is in the same set, not to be included. BF is again in the same set. ED is again in the same set, and EF is again in the same set, and you will find that all the vertex have been included in the set A. That means we already achieved our solution. So what is the final solution? The final solution is we need to make our tree by using these edges. So let us construct our final tree. So we have to take AB. So this is A and AB. Then AE. So AE is here. AE. And then CF. And then this is CF. Now one thing to note here, that when we talk about the Kruskal method, at any point of time you may find that these vertices are not connected. You can see this is one component we have, and this is also we have one component which is not connected. When we work with the Prim's method, throughout the method, when you start working on it, all the vertex will remain connected. Like in this method, uh, like in this case, what we observed, that we started with A, then we have B, then with E, all are connected, but then we have C and F, and now this edge is not connected actually. Okay, so we have unconnected component is also there, or you can say we have disconnected components are there. But in the Prim's method, we don't have this kind of situation. All the time throughout the method, we keep on proceeding and all the vertex remain connected. So this is also one difference between the two methods. Then the next is FD. So FD is this, and then we have BC. So this is what is the final answer. So you can get 1, 1, this is 2, this is 1, and this is 1. So the final answer is 1 plus 1 plus 2 plus 1 plus 1, which is 6. So the MST for this graph is of cost 6. That means you are able to connect all the vertex with the edges whose minimum weight is 6. If you are able to get any other structure with less than 6, that means this is not correct and you did a mistake. So here actually this is the minimum value. You can check with all the possibilities and you will find that the minimum spanning tree for this graph is 6. Now I would also like to show you that there may be many spanning trees, minimum spanning trees are possible for any graph. Now considering the same, I will take this A, F, B, C, E and D. So if you have chosen this AF while you are doing in the ascending order, if you have chosen AF prior to BC, then you would have got this answer, something like this. And in this case also, when you write these values, BC is no, BC is not required. This is not there. This one, this is 1, this is 1, and this is also not required. So that means we have this structure. Just let me remove this part. So this is also one possible minimum spanning tree, and if you look to the cost, so you will find this is also be 6. So here we have also checked that for any graph there are multiple minimum spanning trees possible. So when I say multiple minimum spanning tree, means the structure may be different, but the value that you are getting, that is remain the same. So this is all about the Kruskal algorithm, and we have seen that how it works on any graph to find out the minimum spanning tree. Now the next thing is to analyze that what is the running time, so we can comment on its performance. Now analyzing is always important, because unless you do analysis, you are not in a position to compare the two different methods. Now the next method we are going to discuss is the Prim's method for finding the minimum spanning tree. So we will do the analysis for both the algorithm, and then then only we will be able to find out which one is good. So Next, move to the analysis part. Uh, and this is all about this example. Okay, thank you.